Hello students, in this video we'll introduce energy methods for the wave equation. Let's consider a solution u of xt to the 1D wave equation utt is equal to uxx. I'm just going to set c to be equal to 1. And then what we're going to do is we're going to define several different energy quantities. We're going to define the energy density to be E, which is 1/2 ux squared plus ut squared, right? So we're thinking of kinetic energy and potential energy, right? And then the energy, the momentum density, and the momentum density to be, let's call it P, which is just going to be ut ux, okay? Now here's a proposition. So we have momentum density and energy density for the wave equation, okay? Good. And so here's the first proposition with these things. Proposition. I want to say that ET is equal to PX and EX is equal to PT. And moreover, I know that both P and E will satisfy the equation. Moreover, P and E satisfy the wave equation. Okay, so how are we going to prove this? So let's look at what ET would be. So what's ET going to be? So ET, for example, is just going to be a UX, right? Because the two are going to cancel out. And then UXT plus the T derivative of this thing over here, that's going to be a, two are going to cancel out, it's going to be a UT and then UTT, right? That's what ET is. Let's look at what PX is. What's PX going to be? PX is going to be UTX, UTX over here times UX plus, if I do an X derivative over here, I'm going to have a plus a UT plus UXX. Now those don't look, this looks the same as this, but that and that are different, but since U satisfies the wave equation and UTT is equal to UXX, so indeed those two things are equal. Great. Let's look at EX. What will EX be? So EX is going to be what? EX is going to be just a UXX plus UTX. And what's PT going to be? PT is going to be UTT UX plus UTX. Now these terms are the same, and then these terms over here don't look the same, but they're the same by the wave equation. So that proves that those two things are in fact equal to each other. Okay, let's show that it satisfies the wave equation. So what would ETT be? So ETT is just going to be a little bit of a longer calculation, right? But let's go ahead and do it, right? So what's ETT? Let's do the E one first. I'll leave the P as an exercise, right? So let's do ETT. ETT is going to be UXT plus UXTT, okay, plus UTT plus UTT, like that. And what's EXX? EXX is going to be what? Is going to be UXXX, right? Plus what? Plus what? Plus UXX plus UTX plus UTXX, right? All right, good. And so now, of course, what do we see over here? We see, well, this term over here, we just match terms now, right? So this term over here is the same as this term over here, right? And then what's going to happen over here So I know that this term over here and this term over here are the same because they satisfy the wave equation. So this term over here and this term over here are the same because ux satisfies the wave equation, right? And then what do we have over here? Then these terms over here. These terms over here are the same as these terms over here because u satisfies the wave equation. And finally, I know that ut satisfies the wave equation, so these terms over here are also equal to, so therefore it follows that ETT is equal to EXX, and that E satisfies 1D wave. Excellent. Now, moreover, from these things, what can we do? We can also define the total energy of a system. So what's the total energy? So our total energy of the wave equation is going to be E of t, is going to be E of t, which is going to be 1/2 the integral from negative infinity to infinity of ux squared plus ut squared dx. So do this x integral over here. So this is really just kinetic energy plus potential energy. So this is total, this is kinetic energy plus potential energy. Okay? And that's why we call these things the densities, right? That's the density because this is the density over here inside the integral over here, like a probability density, right? So this, of course, is just like your what? This is like you're integrating your function E, right? Okay, now what's the derivative of this energy? The derivative of this energy over here is what? I can differentiate inside the integral if it's assuming it's smooth enough, right? And so what's going to happen over here is I'm going to have the integral from negative infinity to infinity. The 2's are going to cancel out here. I'm going to have a ux, and then a uxt. Plus a ut, and then a uxx, utt. Okay, good. And so what I can do is the following now, dx. I'm going to integrate by parts on this term over here and put an x derivative over there, right? So if I integrate by parts, this becomes what? This becomes negative the integral from negative infinity to infinity of what? Of uxx ut. And then what? That becomes negative over there, a dx, plus what? Plus the integral from negative infinity to infinity. So I integrate by parts just on this integral. I have to add to this thing over here, utt, dx, right? And of course, this and this are what? This and this are the same, so this is equal to 0. So we've just shown that this energy, this total energy wave equation, is constant. So E is equal to E of 0. The energy, the total energy is conserved, right? So there's a conservation of energy. This is conservation of energy for the wave equation. And conservation of energy will allow us to prove that the solutions to the wave equation are unique. So whenever you have a conservation of energy, that will allow you to prove that solutions are unique. So that's a very useful tool in the uniqueness question for PDEs. Thank you very much.